Old Grumpy Hunter here. Welcome to Acceleration. I had a viewer state,
"My bow has an acceleration of 350 feet per second.
I believe that he meant to say that his bow has initial speed or velocity of 350 feet per second, but this video is the result of that statement. In previous videos I've talked about arrow speed, velocity, weight mass, kinetic energy, and momentum. I've not really talked about acceleration. For this discussion, I'll explain what the difference is between velocity and acceleration, explain how to calculate velocity using time and distance, explain how to calculate acceleration using velocity and displacement distance, explain how to calculate the final velocity using starting velocity, acceleration, and displacement, and explain how to calculate time. If you hang out to the end of this video, there'll be a link for you. Acceleration and velocity are both concepts of motion, and both have something to do with how fast an object moves. Basic definitions for velocity and acceleration are: velocity, the rate of distance of a moving object over time. Acceleration, the rate of velocity change over time change. Here's some more detailed definitions. Acceleration requires a net force acting on an object. Velocity does not require such a force. Every object accelerating has velocity, but every object having velocity does not necessarily have to have acceleration. Acceleration requires a change in magnitude or direction of the velocity. Acceleration is expressed in distance per time squared, for example, feet per second squared or feet per second per second. There are a set of equations called the uniformly accelerated motion equations. These equations assume that there's a constant acceleration during the time traveled. With those four equations, you can calculate initial velocity, final velocity, acceleration, distance, and time, as long as you have three of the variables. Within the uniformly accelerated motion equations, the following symbols are used. All lowercase: U equals initial velocity, V equals final velocity, T equals time, S equals displacement or distance traveled, A equals acceleration. I'll be using the asterisk for the multiplication or time symbol in the calculations to avoid confusion. Back in elementary school, we learned how to calculate speed or velocity by dividing the distance traveled by the time. Speed equals d divided by t. An example would be a car moving 60 miles in 1 hour. The speed equals 60 divided by 1. The speed equals 60 miles per hour. From the equations, we know that velocity can be calculated using v equals u plus a times t. Acceleration can be calculated by rearranging the equation to a equals the quantity v minus u divided by t. As you can see, we have to know both the change in velocity and the change in time, but normally we don't know the time it takes to launch our arrow. For the most part, we know the following information about our bow setup: initial velocity or speed, the arrow at rest; final velocity or speed, the speed of the arrow at the time of launch; and distance traveled, which is the power stroke.
What is a person to do?
There are two ways to calculate acceleration. One was mentioned before, and it requires time. The other does not. Since we don't know the time, we can either calculate the time first, which I'll do in a moment, but without knowing time, we can use the third equation from before: v squared equals u squared plus 2 times a times s, and with some simple algebra calculate acceleration. First, there has to be some rearranging. We need to subtract u squared from both sides to get v squared minus u squared equals 2 times a times s. Then we divide both sides by 2s and reverse the equation to get a equals the quantity v squared minus u squared divided by 2 times s. We now calculate acceleration using velocity and distance. The following calculations will be done with a calculator that goes out to 32 decimal places. I will be rounding the values in both my talk and on the display. My compound bow was rated at 350 feet per second and has a power stroke of 14.125 inches. Using the information about my bow, let's try to run some numbers. The first thing we need to do is convert the power stroke to feet. Next, we put the numbers into the equation, do some simplifying, and we get A equals the quantity 350 times 350 minus 0 times 0, and divide that quantity by the quantity 2 times 1.177, which results into A equals 122,500 divided by 2.354. A equals 52,035 feet per second per second. Wow! I did not believe that number either, but then I had to recall how fast that happens. Furthermore, as soon as the string stops moving forward, acceleration stops. Remember, acceleration requires a net force acting upon an object. But how long was acceleration applied to the arrow? Looking at the first equation, S equals 1/2 times the quantity V plus U divided by T, and again doing some rearranging, we can calculate time. Let me just skip ahead to the final rearranged equation. T equals 2 times S divided by the quantity V plus U. Using my bow again, let's calculate how long it takes the arrow to go from 0 to 350 feet per second. T equals 2 times 1.177 divided by the quantity 350 plus 0. The T equals 2.354 divided by 350. T equals 0.00673 seconds. Now that we know the time, let's calculate acceleration using it. Remember the equation A equals the quantity V minus U divided by T. A equals 350 minus 0 divided by 0.00673. A equals 350 divided by 0.00673. A equals 52,035 feet per second per second. Just for some fun, let's calculate the final velocity using the acceleration, the starting velocity, and the power stroke, or displacement. Going back to the equations, we can use number 3 again, v squared equals u squared plus 2as. You notice that the result in the equation is velocity squared. We'll have to find the square root of v squared. The equation becomes v equals the square root of u squared plus 2 times a times s. Using the results from what I calculated before, I can get the final velocity. V equals the square root of 0 squared plus 2 times 52,035 times 1.177. V equals square root of 104,070 times 1.177. V equals square root of 122,500. V equals 350 feet per second. You can also calculate velocity using time, starting velocity, displacement, or power stroke. The equation is the quantity 2 times s divided by t minus u. I'm not going to talk you through the steps here, but using the information from before, you see how it works out. So far, all the calculations have been based on launching the arrow. But what happens when the arrow has been launched? As soon as the arrow leaves the bow, it's slowing due to drag or wind resistance. You remember that acceleration is the rate of velocity over time change. Since this discussion is not about calculating drag or wind resistance, I'm going to cheat and use one of the online calculators to calculate the velocities out to a few distances. Using a generic arrow leaving the bow at 350 feet per second and with velocities at 30, 40, and 100 yards, we can calculate time and deceleration. Again, we can use the third equation, and after rearranging it to A equals v squared minus u squared divided by 2 times s, the velocity at 30 yards is 337.2 feet per second. A equals 337.2 times 337.2 minus 350 times 350 divided by 2 times 90. A equals 113,703.84 minus 122,500 divided by 180. A equals 8,796.16 divided by 180. A equals 48.9 feet per second squared. Since the arrow is deaccelerating, the value is made into a negative number. A equals negative 48.9 feet per second squared. Calculating flight time is the same as how we calculated launch time before. T equals 2 times s divided by the quantity v plus u. For 30 yards, the flight time is T equals 2 times 90 divided by 337.2 plus 350. T equals 180 divided by 687.2. T equals 0.26 seconds. Without crunching the numbers, here are the results for both deceleration and flight times at 30, 40, and 100 yards. Now you know what acceleration and velocity are, along with the uniform accelerated motion equations, and how to do some of the calculations. I'm going to make it easier for you. There happens to be a website that has a calculator that'll do all the hard work for you. The calculator is called the Uniform Accelerated Motion Calculator. It is found at this web address. The link for it is in the video description. Thank you for watching this Old Grumpy Hunter presentation. Please give it a big thumbs up, and if you haven't already, please subscribe to my channel, and don't forget to push the notification bell.